Hi everyone, this is 5.1 linear inequalities in two variables, and I'm just going to start off with a quick example. Let's first consider the inequality 2x plus 3y is equal to 6, let's say. Now, well, I said inequality, it's actually equality. And in fact, if we were to graph this, well, let's solve for y, I suppose. So if we solve for y by getting y by itself, subtracting turn 2x to the other side, we get negative 2x. Divide everything by 3. What are we left with? Well, we're left with y is equal to negative 2 over 3x plus 2. And we can actually graph this to see the solutions. Remember, the solutions to this equation are ordered pairs. And if you graph this equation, you get a line that has all those points that are ordered pair solutions. So we start at 2. Y equals 2 is the y-intercept. The slope is to go down 2 and over 3. We'll end over here. So we start at y is equal to 2 and then go down 2 over 3, 1, 2, and then over 1, 2, 3. You land from that point to this point, and you get this line. So just imagine that's a straight line for a second. There we go. So this line represents all points that are solutions to this equation. Now we can take a look at an inequality. Okay, so now let's consider the inequality version of this line we just saw, this equation we just saw. And in particular, let's take a look at the less than or equal to version of it. And let's see if we can figure out what this means as far as solutions go. Now remember, solutions to an equation are ordered pairs. Solutions to an inequality will also be ordered pairs. There's also implementing of them, but they're not aligned like these solutions were aligned. There will be an area on either side of this line depending on what the inequality symbol is. And we can kind of see that by plugging in points or by solving for y. I want to show both. So let me solve for y. We already know what it's going to look like because we saw it in the previous thing. But let's see. So subtracting 2x and then dividing by 3. Okay, it doesn't look like much happened. It looks like the inequality symbol is just remained the same. In fact, if you take a look at this and what we got from the previous result, solving for y, it's the exact same thing, only with this inequality symbol less than or equal to instead of equality. Okay. Aside from that, I know that sounds like I went nowhere with that, but you'll see the reason why I'm talking about that in a second. But aside from that point, we can pick any side of this line as a test point. So what I want to do normally is just plug in 0, 0, unless it's on the line, but in this case it's not. So if we plug 0, 0 into the original thing, will it satisfy this inequality? So if x is 0 and if y is 0, what's the result on the left? 0 plus 0 is 0. 0 is less than. So as it turns out, we'll shade everything where that test point is. If it wasn't the case that side was okay, like we plug in a test point and it didn't work, then it's the opposite side that we need to shade. Okay. The next thing is that this line is going to be solid because it is or equal to. So just to explain a little more what I'm talking about is I'm trying to plot all points who satisfy this inequality. Now remember, this inequality less than or equal to is technically or equal to. So points that satisfy it being equal to will be plotted. So namely, this line is going to be included. If it was not or equal to, then we would not include the line itself, so we'd have to dash it. I'll show you a few generalizations of this in a second, but for right now, just know that all we're doing is shading one side of a line, either the lower half or the top half, basically. Okay, we'll see some more examples right now. But before moving on to any next examples, I want to discuss the phenomenon I just spoke about. And I say the following. To graph solutions to the inequality ax plus by is something to see, where that something is any of these following symbols, inequality symbols, less than or equal to, greater than or equal to, or even not straight up not equal to, which to be honest, we don't really see this at all, but it is a possible inequality. We shade either side of the line, ax plus by is equal to c, depending which side contains solutions. So we pick a test point. Normally I pick 0, 0 if it's not on the line. Otherwise you can just pick any point that's easy to plug in. That way you just do a quick plug in and then shade each side of the line. So it's that simple. It's going to get even more simple right now. Okay, this next example is going to be a little different, but let's see if we can solve it with the same technique we used earlier. Now, I'm not saying what I want to do here, but what I'm asked to do really is find the solutions. Now, unlike an equation, you can't just list out the solutions. And in fact, if this is equality, you can't even list out the solutions. You have to draw a line, and the line represents infinity points that are the solutions. Very similarly for inequality, only we're going to be shading parts of the plane. Hard to fathom at first, but after a while you'll start to realize what we're shading represents points that satisfy this. So I'll probably discuss that after the fact, but let's just cut to the chase. And let's see. The first thing I want to do is get that line I was talking about. To get the line, I'm going to pretend this is equality. I'm going to leave it as inequality, but then just in the back of my mind I'm pretending it's equality. So let's solve for y. So remember how that goes. Subtract 5 to the other side, 5x to the other side. Divide by negative 4. Now remember, when you divide by a negative, well, let me just write it out. So when you divide by a negative, the symbol flips. Here, negative over negative is positive, so that's 5 over 4x. And then positive over negative is negative, and that's 2. So for a second, let's just look at this. So imagine that this inequality symbol is equality. Let's graph the line. Okay, here we start at negative 2 on the y-axis. We go up 5 and over 4, rise over round. So go up 1, 2, 3, 4, 5. Then to positive 3, move over 1, 2, 3, 4. We land at this point. Perfect. So now let's connect the dots with a straight line. Now again, points in this line represent solutions to the equation, not inequality, but the equation. So if this is equal to, then all points in this line would be solutions. It's not equal to them. It's greater than. So we can pick a test point, and the point I'm always going to pick as a test point, if it's not on the line, is 0, 0. So we're going to plug it into the original. Plug in 0, 0, x is 0, y is 0. We get 0 is less than 8. That's certainly true. So we shade the side where that test point is on. Okay. If it was not equal to, then we shade the opposite side. So I'm going to shade everything on the side where this test point is on this side of the line. There's another bit of news though. Remember in the previous example, we left the line as being solid, and I said that was only because it was or equal to. This isn't or equal to. It's just greater than. So we actually need to make sure that this line is dashed. The importance of this is we're, again, shading all points, all regions that contain points that satisfy this inequality. So for instance, this point here, which was, by the way, 4, 3, this point is for sure not a solution to the inequality. And I can prove it by plugging it in. So when x is equal to 4 and y is equal to 3, good? Let's plug it in, let's see what we get. We get, well, let's see, that's 20 minus 12. We want that to be less than 8 because that's what the original inequality says, but we get 8 is less than 8, which is certainly not true. So that point is not a part of our solution set, which is why we're dashing it. It was solid in the previous one because it was or equal to, and it would satisfy this because it would be equal to. Okay. Similarly, if I plotted just as an example, it's kind of hard to see it, but this point right here would be the point 1, 3. 1, 3 is in the shaded region and would be a solution, and here's how I know that. When we plug in 1, 3, let me just write it as a point, into the original inequality, we get 5 times 1, which is 5, minus 3 times 4, which is, I guess, 12, is supposedly less than 8. 5 minus 12 is negative 7. That's certainly less than 8, so it is indeed a solution. Plugging something in that is not in the shaded region, like 4, 0, this I'll just do in my head. When you plug in 4, 0 for x and y respectively, you get 20 minus 0. 20 minus 0 is 20, and 20 is not less than 8, so it's not a solution, which is why we're not shading that point. So everything shaded here in red, and again, this line is dashed because we're not including those points, will satisfy this inequality. And now we're going to try our best to generalize this in a, I guess, more organizable fashion. so we can try to get a better handle at doing this even quicker, just way more quicker. So let's see that right now. Okay, so here's an idea I have that'll make the process way more simple, as I was saying earlier. So the idea is that given an inequality in slope-intercept form, in other words, y is isolated, y some inequality symbol mx plus b, it will have solutions to satisfy the following shading. So these are the symbols: less than or equal to, greater than or equal to. So for the less than's, you shade below the line. I'll describe what that means in a second, which is why I put them in quotations. And either they're on or not on the line. If it is or equal to, it's on the line. If it's not or equal to, it's not on the line. So that's what it is for each of these. Now let me just say the following. For the, the not or equal to ones, this is described by a dashed line, as we saw in the previous example. Whereas here, let me do it in black, for the or equal to ones, this will not be a dashed line, but it'll be a solid line. Okay? So dashed would look something like this, dashed or dotted, where solid would just be a solid line. Just like we saw in the previous two examples, and that's basically it. Now this whole below and above situation, basically what you do is you just project above or below and then just shade that region. So, let's just do an example of that right now, and I think we'll understand what I'm talking about. Okay, so from what I said in the previous idea I had, let's solve for y first. So subtract 3x to the other side. Okay, good. Divide by -2. We know what happens. The sign changes because we get a double negative. So don't forget that part, because that part is very key, that the symbol switches. And now we're going to graph this line and do, well, whatever the previous thing told us to do. So to graph this, we're going to start at -3 on the y-axis, because it's our y-intercept. Then we're going to go up 3 over 2. Up 3 and over 2. There we go. So I got this point and this point. Connect them with a line, and then follow the previous suggestion, I guess you can say. And it's less than, so that means we shade below. So I'm going to shade below. But before I shade below, let me ask you, is it a solid line or is it a dashed line? Yes, it is a dashed line, because it's not or equal to. If it was or equal to, it'd be solid, but it's not, so let's just kind of erase accordingly so it looks dashed or dotted, however you want to say it. In my case, it looks more dashed than dotted, but it's fine. So now, again, shade below. So how do we shade below? Pick any point on the line and just go down. So if I pick this point, let's say on the line, and go down, I'm in the below region, so that's below. So I think with the examples I've been giving you, that's enough for you to understand how to solve these kinds of things. And I know when I say solving, it sounds bizarre because we're really just graphing, but it's for us to understand, I think it's enough for us to understand that graphing is solving it, because this is how you would list out all of the solutions. It's just in a visual way, I guess. There are some special cases though. And you may know what I mean if you think about how lines behave. If you have a horizontal line, it's still pretty obvious what's above and what's below. When the line's vertical though, what's above and what's below, there is no above and below for a vertical line. There's left and right only. So we'll just take a look at that one example, and I think that'll be enough for this section. But let's see that right now. Okay, so these are some of those two extreme cases I was talking about earlier. One of these is vertical and the other one is horizontal. Let's see if we can remember that. So first let's consider the equality versions of these. So consider the graph for the equation x is equal to -4 and y is equal to 3. First, let's start with the first one, of course. Now, x is equal to -4. Well, first we'll go to x equals -4. So we don't really need to dash everything, but -4 is over here. And the line x equals -4 is the vertical line that passes through x equals -4. So the best way to think of it is that you just go to that number on that line, so x equals -4, and then just draw a line that's not that axis. So don't draw an x-axis, draw a vertical line in this case. Now this is x is bigger than -4. Numbers bigger than -4 are on the right, and even then, look at this. If x is written on the left like this, then it basically says, well, shade to the right. So it's pointing to the right, which is nice. But yeah, if you think about it, it just says all values of x that are bigger than -4, and that's all of these. Even more than that, it really says any point that satisfies that. So we're really just shading this whole right side of this line. And yes, it is a solid line because it is or equal to. So that's how easy that is. It's just left or right, depending. Just kind of think about what it means and then shade that side. Okay, getting to this one now, y is less than 3. Well, y is equal to 3 is a horizontal line that passes through y equals 3. So there's y equals 3. And again, you don't really have to dash any other or mark any other access coordinate point, but that's fine. And then this is less than 3, so we're going to shade all y values below this. And it's not or equal to, so it's a dashed line. And remember, the fact that it's less than means you shade below, so shading below makes sense, no matter how you think of it. Okay, like I said, I thought this would be enough, but there's an application problem I'm seeing in the book that I think we deserve to see. Let's see that right now. Okay, so for this problem, we're asked to not only set up the inequality, but also graph. Let's read. So it says, seed costs for a farmer are $90 per acre for corn and $70 per acre for soybeans. How many acres for each crop should the farmer plant if he wants to spend no more than $11,000 on seed? So again, there are infinitely many solutions. All we're going to do really is just graph those solutions as a region on the XY plane. And there's something interesting that happens, but I guess the first thing that we can do on this screen here, I guess, is we can label corn as, let's say, X and soybean as Y, and this will be the total amount, so let's keep that in mind. And in fact, I can give you the inequality right now. So if you're spending X amount of corn, $90 per acre, how much money are you spending? Well, so if you're buying X acres of corn for X acres of corn for $9 per acre, how much money are you spending for that X amount of corn, acres of corn? It's weird to say that out loud, but the answer is 90x. $90 times however many acres of corn you're buying. Again, sounds funny, but that's what it is. And similarly for soybeans, it's going to be the amount of acres multiplied by its cost per acre, which is 70y. So 90x plus 70y is the total amount we'll be spending depending on what x and y are equal to. And we want this total amount to be less than 11,000 because it says no more than. No more than applies less than. No more than, I guess, is less than or equal to. Another way of saying this is at most, no more than. So not more than this, but equal to this is okay. So less than or equal to 11,000. The other key restriction here is that, well, maybe kind of obvious, but x and y are each going to be greater than or equal to 0 because we don't want negative values of corn and soybeans. And the book actually hints at this for this problem because it says include any non-negative restrictions, and these are the non-negative restrictions. So I'm going to erase all this, and then I'm going to have this a little higher up, and then we're going to graph this and see the solutions. Alright, so now we're asked to graph this inequality, and I was going to do this by isolating y like we have been, but in this particular case it's best to find x and y intercepts. And the reason is that when you find the y-intercept by isolating y, since 70 doesn't go into 11,000 evenly, you won't get an integer, and it's not very easy to graph. Also, these numbers are kind of large, so let's just do it this way. To find x-intercept, remember what you do, you set y equal to 0. So in this equality, if it was equal to, we would get 90x is equal to 11,000. Divided by 90 gives us x is equal to, the zeros cancel, 1100 over 9 with my calculator, I'm getting about 22.2. Okay. So now for the y-intercept, we set x equal to 0, and in setting x is equal to 0, we get 70y is equal to 11,000. Dividing by 70, I get y is equal to, let's see, the zeros cancel, 1100 over 7. In my calculator, I got about 157.14, let's just say 0.1. And now let's attempt to graph these. I'm realizing this was 122. My mistake. You can use your calculator, but these are the numbers you should get. So I'm going to try to make this to scale, but it may not be to scale. So here the y-axis represents our soybean crop, number of acres, and then x is the number of corn acres. Okay, so the x-intercept is 122. So let's, to make this scale, let's go by 50s. Yeah, I think 50s is okay. So let's say that's 1, 2, 3, 4 50s. 1, 2, 3, 4 50s. So 122 would be in between 100 and 150. It's going to be a little less than halfway, just to make it somewhat to scale. And then this is going to be 50, 100, 150, that's 200. 157 is a little bit above 150. So that's our y-axis, our y-intercept. Y-intercept, x-intercept. Now let's connect them with a line. It is a solid line because it's or equal to, so keep that in mind. Also, it's less than, so we're going to shade below the line. So let me do that in red, shade below the line. Now, I am also going to keep in mind that our y values and x values are to be positive. So I'm not going to shade any negative y values nor any negative x values. And in fact, that this triangle is really what we get as our solution set. Any point in here will actually satisfy this inequality. And just to pick a pretty safe one, as an example, this point right here is clearly in the triangle, and this point is 50 for x and 50 for y. You can see by plugging them in, 50 times 90 is 4,500. 50 times 70 is 3,500. And when you add these, what do you get? You get, well, I'm getting 80,000, or 8,000. And that is certainly less than or equal to 11,000. That's less than 11,000. So it satisfies this inequality. Perfect. That's just an example of what we're doing. Okay. Now, again, the only thing it's asking us to do is what we just did. Find the inequality setups, including the restrictions of non-negative numbers. Perfect. And then graph the solution set. And that's this red region here, including the line that I made in solid. I guess these are included as well. Also solid because greater than or equal to 0, it's possible you could buy no corn or no soybeans. Like for instance, any point on this x-axis line would work. That means you're not buying any soybeans but only corn. If you buy less than 122.2 acres of corn, then it would satisfy the inequality. And perfect. That's it for this example, and that's it for 5.1. And we'll move on to 5.2. I'll see you in the next video. Thanks for watching.